Thanks for taking this course and making it all the way to the end. In these last few concluding slides, we want to just briefly remind you what you've done, talk about some conceptual relations to other issues in cognitive science and deep learning, and then conclude with a few open questions.
So let's recap what you learned today. You learned about operators and the use of vector symbolic algebras, generating vectors, bundling, binding, and cleanup. You learned how to use VSAs to implement simple analogies, to learn and generalize on the Wason and card sorting task, and using error-driven learning in combination with these representations to do so. You learned how to impose an inductive bias and achieve sample efficiency, and how to build a spiking question-answering network.
So going through all of those components of the tutorial was in the service of introducing neurosymbolic methods. And one of the things that we find most compelling about these methods is that they combine the advantages of traditional symbol-like processing with neural network-style processing. What we want to talk about on this slide is some of the broader conceptual consequences of being able to leverage these advantages together.
We can address the symbol grounding problem because our symbols are vectors, the language that neural networks naturally speak, so we can relate them directly back to sensory inputs through the activities of neural networks. This is important for building AIs that have sophisticated understanding captured by their concepts. Large language models, for instance, have abstracted language representations, but struggle because these are often disconnected from the world the representations are about.
As well, generalization is something that we get a new kind of perspective on. In general, we've seen how to explicitly encode an inductive bias. There are two specific ways we can capture inductive bias.
One way we can capture inductive bias is by working with representations that are locally smooth, which is to say points nearby in vector space can have similar meanings, a result we often see in generative models.
Coupled with those kinds of neural network advantages, we also get inductive biases that are the result of symbols being able to be composed to generate new symbols. This kind of compositionality is something traditionally thought of as being important for cognition, along with features like systematicity and productivity. As a result, when we build architectures and models using this approach, we're able to capture these kinds of structure-dependent features of cognition as well.
We also wanted to address some frequently asked questions that come up about these representations. For example, what is the relationship to deep learning? Luckily, these representations are all differentiable, and they work well in deep learning frameworks. These are complementary approaches.
In this tutorial, we have avoided continuity, as our representations have largely been discrete. But our bonus material shows how to apply these methods to continuous spaces, like those found in cognitive maps. Interestingly, those methods apply to time as well. In short, we can import a lot of the same techniques when building networks that are representing information over time. And critically, this contrasts with standard techniques like LSTMs and RNNs, where time is usually discretized in a somewhat arbitrary manner.
And what about representing uncertainty or probability? Well, we've done a bit of work towards this end. It turns out that all these continuous representations that we're building have an implicit relationship to uncertainty and probability, and that's one of the directions we're taking this work in next.
If you're interested in more information on how we've used these techniques in past work, we have this book, How to Build a Brain, that covers a lot of the examples we've used here and many more in-depth ones, including Spawn. We also have a website at compneuro.uwaterloo.ca that links to papers, code, and so on, all related to these topics. We'd like to conclude by thanking you again for taking the time to look into neurosymbolic methods, and we hope you found this tutorial useful.